Hello everyone, let's solve this fluid mechanics problem. Here we have a setup where we have two immiscible fluids of equal density that are flowing down a surface that is inclined at an angle theta. Right here we can see our sketch. We have fluid 1 and fluid 2. On the bottom, fixed surface. On top we have a free surface. Okay, each fluid has a thickness of h and they are equal. We also know that we have equal and incompressible densities, but the viscosities are different. Viscosity for fluid 1 is mu1 and for fluid 2 is mu2. We are also dealing with a steady state setup, and they want us to find the velocity at the interface right here between the two fluids where y is equal h, and they want us to find the velocity at the free surface where y is 2h. Okay, we're gonna have a coordinate axis set up right here. X is pointing downhill, and therefore this way we can simply analyze this as a one-dimensional flow in the x direction. Here's our body force setup. The only body force that we are considering here is gravity, and its component in the x direction is gx, where g times sine theta. Okay, all right. Since this is a very long problem, I'm gonna try not to go into too many details because otherwise it's gonna be an hour-long problem and nobody really wants that. Okay, so let's get started. In order to figure out velocity profiles, we need to work with our conservation of momentum, otherwise known Navier-Stokes, right? And to cancel some things out, we're gonna ask for help from the conservation of mass equation. So we have two fluids, fluid 1 and fluid 2, and each of them is gonna have its own velocity profile. Therefore, we're gonna have to solve the conservation of momentum for each fluid separately. When we're gonna get further along solving the problem, I'm gonna show you a little shortcut, but as of right now, just so we can understand it easier, that's what's happening. Conservation of momentum, solve for fluid 1 and solve for fluid 2. Alright, let's get started. Fluid 1. Here it is, the Navier-Stokes equation written up for the x component. Okay, let's cancel some things out. They said steady state, therefore we can cancel this guy out. We have a one-dimensional flow flowing only in the x direction. We do not have any molecules going in the y direction or in the z direction or any of that. Only x direction, right? So therefore one-dimensional flow, we can cross v equals 0, and we can also cross w, which is equal to 0. U we cannot cross out because it's not equal to 0, right? But this guy, let's take a look at this term right here. For this one, we're gonna go to the conservation of mass. Here it is, the incompressible form, and we can see the three terms. This one and this one we can cross out. As we discussed, we're dealing with a 1D flow, one-dimensional flow, and all we have left is this one right here. Change of u with respect to x. That's exactly what we wanted because it's gonna allow us to cross out this term. Now, mathematically speaking, if the derivative of something is 0, then if we take another derivative of it, that'll be also 0. Therefore, this term also goes to 0. The very last term, we are analyzing this in 2 dimensions, x and y, and it's a one-dimensional flow. Therefore, bye-bye. We can cross this guy out as well. Now, we have a free surface on top, so we cannot have a pressure gradient in the x direction, so we can cross this term out due to free surface. Okay, so now let's do the same for fluid number 2. We wrote up the Navier-Stokes equation, cross things out, conservation of mass helping us again, and as as I'm pretty sure you can tell that everything on the left hand side is the same thing as it is on the right hand side. Okay, this is exactly what's going to help us figure out a shortcut, which I will show you in a minute. As of right now, let's continue solving it for both fluids. Okay, here it is. I copied and pasted up here so we can see what we did on the previous page. And let's see, everything that we could, we crossed out. So let's clean it up. For the first fluid, let's continue working on the first one. On the left hand side, we have everything crossed out. Therefore, we have a big fat zero. On the right hand side, we have the body forces plus kinematic viscosity times this second derivative term. So, they didn't give us anything about kinematic viscosity, right? They told us that the dynamic viscosity is mu1 for fluid 1 and mu2 for fluid 2. Therefore, I'm going to multiply this equation with density, and that's going to allow me to change kinematic viscosity to dynamic viscosity. I also plugged in the body force, which is the gravity, but only the x component, which is g times sine theta. Okay, let's rearrange some things. I moved the second derivative on the left hand side, and I collected all the constants on the right hand side. Now, we are interested in u by itself, right? Because we need the velocity profile. But in order to get there, we need to take an integral of this equation of both sides with respect to y, and we need to do that twice. Okay, so first integral is going to give us equation number 1. Take another integral, and it's going to give us equation number 2. And this is the the velocity profile of our equation, right? Our flow. This is the general solution, mathematically speaking, of this differential equation. Okay, so I'm going to call this equation 1, equation 2. Now let's take a look at our second fluid. Same thing, clean it up, write up what we have left, take the two integrals and arrive to the general solution. And again, I'm pretty sure you can tell that this side is exactly the same as this side, right? And this one is where similarities will end. So u here and u here are the same. Therefore, you could have taken a shortcut and don't even bother doing one of the fluids, right? Because whatever you got here is valid for both fluids. So this equation right here describes both flows, okay, as of right now. But as we're gonna proceed, this is the point where the similarities will end, because from now on we're gonna have to figure out these constants, and we're gonna have to figure out separate for each fluid, and the differences will come from the boundary conditions. Each fluid has different boundary conditions, right? One is at the bottom, one is at the top. They have different boundary conditions, okay? But before we do that, let's make these more specialized for each fluid. Okay, this is exactly the same thing what was on the previous page. This is where we ended up. And we said that we could simply ignore this side. And as we arrived here to this general solution, now we break it up for fluid 1 and fluid 2. We're going to make it more personal to each fluid. So for fluid 1, and on the right hand side, fluid 2. For fluid 1, I'm going to replace the general U with U1, and the dynamic viscosity will become mu1, because they said that that's what it belongs to the first fluid, right? Also, our constants, they're going to be individualized to each fluid. Here, I'm going to call them A1 and B1. Same logic for fluid number 2. U will be replaced by U2, mu2, and our constants will be renamed A2 and B2. Okay, now these equations became more personal to their own fluid. Here it was general and it was available for both. It was describing both of them at the same way. But now we individualize them. Okay, and this one is going to help us figure out what we need. But first we need to figure out our 4 unknowns, right? A1, B1, A2, B2. And in order to do that, we're going to need 4 boundary conditions. We're going to need 2 boundary conditions that will belong to fluid 1 and 2 boundary conditions that is going to belong to fluid number 2. All right, it is boundary condition time. So our 4 boundary conditions. Let's start with our number 1 right here. I'm gonna take this location right here where y is equal to 0, and because of the no slip condition we know that u is equal to 0. Now this location has nothing to do with fluid number 2, right? It is right here on the free interface between the solid surface and fluid number 1. Okay, and our second boundary condition that I'm going to rely on is right here on top of the second fluid at the interface where it meets the air, let's say, right? Which is the free surface. Here y is equal to 2h, and we know that the change of u with respect to y is equal to 0. So let's work with the first boundary condition. We're gonna take this boundary condition and use it with the equation number 2 for fluid 1. I rewrote it right here just so we can see. Plug information in from the boundary condition, and that's gonna help us find that B1 is equal to 0. This is our first unknown that we have determined. Very good. All right, let's proceed. Using our second boundary condition, I'm gonna use the first equation but for fluid number 2. I rewrote it right here. Plug this information in, and we are able to determine our second unknown, A2, right here. 2h rho g sine theta over mu 2. Okay, we have 2 unknowns determined, we still have 2 undetermined. Therefore, we need 2 more boundary conditions. The third one, I'm going to take a point right here on the interface between the 2 fluids. Okay, here we know that y is equal to h, and we also know that the velocity of 1 is equal to the velocity of 2. So imagine it in such a way that the very last molecule of fluid 1 is stuck to the very first molecule of fluid 2. They're kind of stuck together. They are moving in nice as a pair. Okay, that's why, of course, as we would go further and further away from the interface line, this will not be true anymore. The velocities will not be the same. But where they meet each other, this stands. Okay, and this is what we're gonna utilize. So we're gonna do exactly what this equation asks us to do. Take U1 from fluid 1, which we can also see right here, right? So I'm gonna take this one, put it on the left hand side, and I'm gonna take the equation of U2 and I'm gonna put it on the right hand side. At the same time, plug in H for Y. We can see it right here, 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 and here. Okay, do a little algebra, and B2 is equal to this whole enchilada right here. But unfortunately, we can see that there's another unknown hiding in it, and that's A1. Therefore, as of right now, this is a dead end. We're gonna need to figure either A1 or B2 out before we can maybe come back and utilize this for something. But as of right now, we need to abandon it, put a pin in it. Okay, let's continue trying to figure something else out somewhere else. Therefore, let's take a look at our fourth boundary condition in the same location on the interface between the two flows. Here y equals h, and we also know that the shear stress of 1 is equal to the shear stress of 2. Now, the generally written up, the shear stress formula is dynamic viscosity times change of u with respect to y plus change of v with respect to x. Because we have a 1D flow, we can cross this guy out, and all we have left is this one, the dynamic viscosity times change of u with respect to y. Now this is general, so I'm gonna write it up separately for both fluids. For fluid 1, shear stress 1 is equal to dynamic viscosity 1 times the change of u1 with respect to y, and here shear stress 2 is equal to dynamic viscosity 2 times the change of u2 with respect to y. Okay, so let's come back here and do what this formula tells us. Put shear stress 1 equal to shear stress 2. Okay, mu1 times this right here. The change of u1 with respect to y is equation number 1 for fluid 1, right? We can, and this one is equation number 1 for fluid 2. And this one we can also see right here. We already used it for something, right? So that's what we can see here. This is equation 1 for fluid 1, and this is equation 1 for fluid 2. Okay, put them equal to each other like this says. There it is. Do some algebra, and we are able to see that A1 is the only unknown. Therefore, we just determined our third unknown, which is A1, and that is 2h rho g sine theta over mu1. And very good. This is what is going to help us come back right here to the equation that we abandoned a minute ago, and we can plug it in, and once we do so, we can figure out B2. And after a little algebra again, we can find that B2 is equal to this right here, 3 over 2 rho g h squared sine theta, and in parentheses 1 over mu1 minus 1 over mu2. Very good. Now we have all 4 of our unknowns, so we can proceed to go back to our general solutions and update them. And this way, there's no more unknown in it, and they become the particular solution of our differential equation. Okay, so we determined the velocity profile for the first fluid and the velocity profile for the second fluid. Very good. All right. And these two are the ones that are going to help us figure out the requested velocities, right? Because they asked us to find 2 specific velocities. First one, they want us to find the velocity at h, where y is equal to h, at the interface where the 2 fluids meet. Okay, for that, I'm going to use equation 2 for fluid 1. This one right here, right? And what do we have to do with it? We need to plug h into the location of y, and that's going to give us the value for u1 at the interface. So that's all we do. Take the equation, plug in h, clean it up, bam, there you go. This is an actual value. There's no more unknowns in it, right? Every single value is considered known. So there it is, our first answer. Now they also want to find the u at 2h, and this would be on top where the second fluid meets the free surface. Now we can't use this again, right? Because the jurisdiction, so to say, of this equation goes from 0 to h, just going across the first fluid. Going across the second fluid, we need to rely on this. And the free surface, the 2h location, will be part of this. Therefore, we need to take this equation, plug in 2h instead of y, do a whole bunch of algebra, clean it up, factor out all the stuff that is common, and here you go. Finally, we arrive to our answer, where u at 2h is rho g h squared sine theta, and in parentheses 3 over 2 mu1 plus 1 over 2 mu2. There it is. The two final answers for our long problem. Hopefully nobody fell asleep. And if you enjoyed it, please give a thumbs up to the video so other people can find it, and have a great day. Thank you.